we are in the middle of the break.
Okay.
So you have time to adjust yourself.
Mm-hmm.
Unfortunately, it's very hard to catch up when you're like in the middle of the practice session.
Mm-hmm.
Because
Okay.
everything is like this, the one flow, right? So if you're
Mm-hmm.
like in the middle, then it's in the middle. So what you need to do is need to start from a New York taxi data set, what we have done yesterday.
Okay.
And so first you need probably to run the setup in the top of the file, right?
Mm-hmm.
So in the top of the file, there is a setup. You need to rerun it. And then you need to run this New York City dataset thingies. So let me show you this. Yeah, so this cell, and this cell, so that downloads the files, right?
Mm-hmm.
Yeah, and then you have to run the Kaggle setup, exactly
Mm-hmm.
what we have done yesterday as well.
Okay.
So you could do it. There will be a mistake in the CP line, but you need to, go on until the next line and then go back, and then it will
I
work.
remember. Mm-hmm.
And then you need to make sure that you have accepted the Kaggle competition rules. So
Mm-hmm.
if you go to the Kaggle competition and you click on late submission, it will have a dialog where you should click yes, I agree.
Mm-hmm.
So Kenneth, if you're listening to this, these are the things you should probably do as well to catch up. Hey, I think you're muted at the moment, but all right. So then if you run this line here, you will get in the leaderboard, in your submission, my submission page, if you go to my submissions, here we go, then you should see that there is a new submission if you run this line. And then you just have to run through this read in the New York City data section. Basically just click until the naive baseline. So in naive baseline, there are a couple of things that we have done together with everybody else.
Mm-hmm.
You can share your screen and I can just help you to go through that. Like we did for Igor, for example. He was a bit late, so we kind of caught him.
Oh, thank you.
No worries. I was just saying that Lena can maybe share her screen. I stopped sharing my screen, and Lena, so you can share your screen, and then we can just help you to do the step-by-step stuff.
Maybe I need a moment to do some stuff, and then
hide all the stuff, all the secret stuff. University of Toronto secrets.
By the way, you have great background today.
Yeah, this is my team. I'm part of the team, which is autonomous self-driving. It's not that I'm heading this team. By the way, this guy is heading that team. So this guy here. I'm one of the VP leads of this project. So we are very proud of our car. This is our Dark Knight that is going to be self-driving. Well, not really. We are just researching the self-driving opportunities. So this is our test bed. But yeah, if you can share the screen, we can guide you through and make sure you're at the same page. I hope you got some sleep yesterday.
I hope to.
So shall I share my screen?
Yep. So it will be okay, but if you can give me a sec.
So if you open the Slack And in the Slack, I posted the code lines for this cell, for the naive baseline cell, and for some other stuff.
Okay.
For example, I'll send this one as well to Slack. Okay. Oops, this was not really good. Kenneth, how are you doing today? This is the. We can't hear you. You're muted, so I can unmute you, but.
Just trying to catch up here. Apologies for not being.
No problem. No problem. So.
For some reason, this class was not on the KSE calendar for some reason.
Yeah,
I knew very well that it was happening today because we talked about it yesterday.
Yeah,
oh.
yeah.
Oh, you have it on yours.
I have it on mine, so I have added it.
There is no entrance for today.
Okay, okay. I there might be some trouble. I just wanted to say, so do you need to rerun the setup here at the top of the screen here at the top of the file? Just to get all your NumPy and pandas and all that kind of stuff. And then you just have to run through the data, New York data part, which
I'm in the Kaggle token section.
Oh, you're in the Kaggle token section. So this one, right? So there will be a mistake at the CPU line, but you need to go on and then just have to go back and rerun that. That would be okay. And then in order to make sure that everything works, you need to go to the Kaggle webpage. And when you click on the late submission, you need to accept the rules. And if you go back and you run this Kaggle competition submit, it will send a submission file to Kaggle. And you should see at the My Submissions page, the latest submission. So you should see a submission.
So when I download this Kaggle token, do I need to upload it then to the
No, so you need to open it up. So you need to open it up. So I looked it up here. Okay, you can't see it, but so my file says that it's just username and my key. So I copy my username here, and I copy my key here, and that's all. That's all there is.
That's all. Yeah. Okay.
When you run this cell and then you run the next cell, it will tell you something like, oh, I don't know, or something is missing, but that's okay. If you go to the next cell and then go back, it will be fine. It will run without mistakes. And then you just have to finish it up.
So that's what the mistake is. The mistake is
sorry.
Bless you.
Sorry, I need to mute my mic.
No worries, Sigurd. Yeah, so if you have a mistake at the CPU line, then you just have to run the next line with the Kaggle config. And then you need to go back to the CP and then just run all the way through. Lena, where are you?
Good question.
My page just crashed.
Oh.
Okay. I will.
Lena, any help needed?
Just give me 5 minutes.
Unfortunately, the problem is I don't have 5 minutes to give you.
Okay, so I can follow up you.
Hey, go ahead.
We need to go on and because we were quite ambitious to finish up the supervised learning today, but so the thing is, if you guys manage to do the Kaggle key and the keynote submission here, the first submission, and then you just run through this read in New York City data, it's just running them through. So it's a pre-processing that you need to do to clean up the data set. And then you do it until naive baseline. The thing is, you can skip this naive baseline until where we are. And we are at the linear regression based on more than one feature right now. So we are at this linear regression based on more than one feature. All right, so everybody else, welcome back. And now that we have suffered enough with one feature-based linear regression, you remember that we created two features, which was APS difference longitude and APS difference latitude. So now we can finally use both of these to train a linear regression, right? So we use the same scikit-learn function linear regression. We initialize linear regression, and then we take both of these features in, right? So we just use both of these features. And then we use them to predict fair amount. So here we go. Yeah, so what difference can you see? What is the most important difference? Sivan, what does catches your eye?
So now I see two wanted intercepts and two W ratios.
Exactly. We have two coefficients now, W1 and W2, right? So one of them is a longitude, how many dollars you need to pay for 1 degree in longitude, and the other one is how many dollars should I pay for every other degree in latitude, right? And our intercept has changed. Oleg, did it increase or did it decrease?
Hello?
Yeah.
As far as I remember, it's decreased, I think.
So yeah, it decreased from something like $7 to 6.1. Right? So now we have to pay less just to get in the car because we have explained a little bit more from the other features. So now we can make this new submission. So now we have 3D linear regression, meaning that we have two independent variables and one dependent variable. So we have 3 features in total. And we can make this submission file. Here we go. Can you guys submit this to Kaggle and tell me what's the score? How much did we improve? You remember that the previous one was 6.06. Igor, what's the improvement of this new linear regression?
Don't know right now. Let me check.
Please do. And you remember that the goal is the top 100. And please let me know if we are at the top 100 so we can finally go home and have some beer.
Yeah, for 5.7, a bit better.
A bit better. But does it make it into top 100?
No.
Oh, again. That's sad. That's so sad. But where we are, like 500?
1,281.
Frustrating, very frustrating. 1,000, we are still not even in the first 1,000 of the submissions, right? Out of like 1,400. That's frustrating.
To be on top 100, we need a score less than 2.9634.
All right. Challenge accepted. You know what? Challenge accepted. I'll do it. Let me show you how I'm going to do it. Now we moved on to the section with the decision tree. Okay, decision tree we have been discussing yesterday, so it should be easy peasy lemon squeezy, right? So what happens that we use decision tree regressor. We set the max depth of 100. Let's set max depth of 100, and let's use this training data. Here we go, the training data. And here we also predict the train data fair amount, right? So, so this is exactly how we did the linear regression training. So first we say, what are the independent variables? And here's this one, what is the dependent variable, right? So this is exactly what we have done before. Nothing new here. Here I'm asking, can we predict, so instead of submitting to Kaggle all the time, can we say how good our model is? Can you tell me what is, so with this line, can you please calculate RMSE on the training data? So we have a DTR, right? DTR. Can you predict the fair amount on the training data and calculate the RMSE? So in order to calculate R, you need NP SQRT. can you predict the RMSE on the training data of this DTR model? Please do it here. I'll give you a couple of minutes to do it here. And in the meantime, Lena and Kenneth, where are you guys?
I'm at save load model using Pickle.
Okay, save load Pickle. You don't really need to click through it. You just, you can jump to, for example, linear regression based on more than one feature. You can click through this one and check out the leaderboard. Check out your My Submission page to see that you have actually submitted this new submission with linear regression with 2 features. And then go and join us at the decision tree. Lena, where are you?
I have problem with my Kaggle ID, so I have no idea.
Can you share the screen? I have to stop my sharing,
Okay.
so can you share the screen?
Okay. I hope this one.
It's yeah. Just
So I've made 2 submissions. So, and the leaderboard is just to find yourself.
Lena, this is the downloading file, right?
Okay. Yeah.
You stop sharing.
Okay.
So did you run? So when you run the authentication, what did it say?
Like this file not uploaded
No,
error.
the previous cell. Okay, let's
I
see
don't know.
what happens.
Nothing.
Okay, that means basically that there was some misconceptions. Can you click on runtime up there in the menu? You have insert tools and then runtime. Can you click on basically interrupt execution? Restart runtime. You can also restart the runtime. Yeah. Can you click on? Can you go up? Yeah. So sorry. Stop. That was too quick. So New York City taxi. New York City taxi.
Okay.
Yeah. So the first cell. Yeah. Here. Click on that one. Okay. And now on this one. As soon as the previous one stops. Okay. Let's do it. Stop. Okay. This doesn't work. Okay. You need to really you need to really open the new incognito window, perhaps. I'm not sure if that will work either. Let me see. So when you use this cells, you click too many times, or you rerun them many times. Factory reset the runtime.
Am I looking for public leaderboard or private leaderboard for myself?
It doesn't. You can go for public. I think it's fine.
It says I've made submissions, but I can't see them on the.
So you won't see them because the submission is closed. So all you can do is just to find yourself and tell us where would be the place if you would be on the leaderboard.
Okay. So I've done all that then. I'm ready to go.
Yeah. So Lena, I'm just thinking, what can you do about this? What if you run the LS down there? So
just
the cell after the next cell?
After this one?
No, it's just the cell down there, below download. There is another cell. Yeah,
Okay,
this cell. You have it. Okay, so you have New York City data. So it was false alarm here. Okay, run this one. So it unpacks all the files. Good. Did you download your API file?
Yes.
Kaggle.json. So you need to insert your Kaggle username and your key inside these inside these gaps.
Okay.
Okay. And now run that. This will be a mistake, but you run the next one and then go back. Okay, run this one and now go back, and now rerun the 9. And now rerun this one. And now you have to, did you accept this rules on the Kaggle page? Okay, then run this Kaggle competition submit. So now go to the Kaggle competition page, my submissions. And so you just submitted the sample submission. So now you just can go on until, go back to this one. So this section, read in New York City data, just click through the, oh, you didn't have a PD because you didn't rerun the setup. Okay, but stop sharing and I'll get back to everybody.
Oh, okay, thanks a lot.
All right, everybody. Did you guys code it in here? So Oleg, tell me, what should I type?
You should type, wait a moment. Just going through the code. I can copy.
You should be able to explain. So we have DTR. So we have DTR. DTR has the function predict, right?
Yes. Wait a moment. I have it just. I just was searching through the code here, and now I lost where I was in my. Okay, it's better to look for the DTR. Yes. Okay. DTR.fit. Dot predict, and then test df, and we shall take columns.
No, I wanted to have train. I wanted to have train all this stuff. So on train, what would be the score on train? So if I predict on train, so I use the same stuff that I used to fit the model to train the model. To predict the model. So now I use DTR.predict, and then I use the same features as I have used to train the model. And now I can say, all right, so how do I calculate RMSE? So I know the true values. So here are my true values. I now have an array of predicted values. What is RMSE? Simon, what should I do here?
I think we should put minus here.
Minus, all right.
Yeah,
so we should find the difference.
And we should put it in square, first of all.
Yeah, we should square it. Okay. And
take a root. Yes, sum. Sorry.
Sum or MSE, mean square error.
Yeah.
So it's mean, right?
Yeah.
Not the sum.
Not
and then
the sum,
we can
I agree.
And then we can take a root of this. So just make sure that it works. No, it doesn't work because I missed, I probably had too many brackets somewhere or not enough.
I think we need one.
Okay, we need one more, all right.
One more.
Oops. Okay. Unable to coerce series length must be 1. Okay, just give me a second. I guess I remember there was this kind of problem. I think this is a trouble of working with data, pandas data frames and NumPy arrays at the same time. That's okay. No, it's actually fine. Okay. So you will see how to debug that kind of stuff. I'll just, so now we will just look back and say, okay, what if we just find a subtract? Okay, it doesn't really subtract. It does this work. Okay. This should be working. Okay, this is working. Train their amount. Let me see if this works. So it has the problem with a number of brackets that you put around it. Sometimes it works with one pair of brackets. Sometimes it needs two pair of brackets. For example, right now I needed two pair of brackets. This is annoying. That's what pandas is all about. And then you need to have NP mean around it. And I'll send it to Slack so that you guys don't have to, you know, spend all your time thinking about how the hell these things should work. Yeah, so now we can put it inside the square root. Okay, sorry, I just copied the one without square root, but in fact, you need the one with the square root. Yeah, so, okay. Okay. Now it's NP SQRT around NP mean and so on and so forth. Igor, you remember you told me that we needed 2 point something to get in the top 10, right? Did you say something like that?
No, I told 2.9. Actually, we are better than top.
You see? Yeah. You see, I kept the promise. We just, if that is true, well, sorry for that. So this is, I can't, yeah, I should just delete this one. So if that is a true score, we are in the top 100, okay?
Mm-hmm.
Are you guys happy? We are in the top 100. We have just been in 1,200 something.
Can you please copy paste the code from NP mean into the chat right here?
Yeah, sure. Sorry, I have forgotten. Yeah. So Oleg, are you happy?
Very happy.
So do you trust the score? Do you think we are as good as I'm saying?
Let's check. Let's upload and check.
No, wait. Let's, Simon, are you happy? Let me collect the opinions.
I'm very happy, but I think we should find a way to test our model on test set.
Okay, that makes sense.
But yes, I cannot stop smiling.
All right, that makes sense. Okay. Kenneth, what about you? What about not being able to stop smiling? Do you relate to that?
I am suspicious, mostly because of the form of your lecturing has trained me to know that when you ask these kinds of questions, there's something I haven't.
There's something fishy going on here. But about smiling, I think it still makes sense. But you're absolutely right. I'm trying to get you into trap, but I mean, obviously, you guys know that I'm leading you into trap.
If I may, if I understand the problem is that we applied the decision tree.
Yeah.
Pure decision tree without any regression. It means
without well, we are doing regression with the decision tree.
It means that the max depth of our tree should be very big.
Yeah, it's 100. It's like a lot. It's a very deep tree. It's super deep tree. But Igor, what is the most suspicious thing about this score about 2.59?
It's the same. Oh, sorry.
Actually, we did not do anything. Well, from my point of view, we didn't do anything
Wrong. Everything is right.
No. I mean, actually, we had regression model with two parameters.
Two features.
Yeah, two features. Actually, now we do decision tree
On two features.
Well,
this is
yeah,
still two features.
Same. This is the same, but accuracy of the model is 2 times better. It's like, I don't know.
3 times better. 3 times better.
Yeah. That's really suspicious.
Okay, so you also feel suspicious. Kenneth, you wanted to add something to it.
Yeah, if I run the line of code with the square root and without the square root, it ends up with the same number, which seems strange.
That is strange. So let me remove the square root here and just show you that it will be 6. It is 675.
Okay.
So there is some small problem there. Igor, you wanted to say something?
Yep.
I mean, I do agree with you guys that this all looks very suspicious, but what is the most suspicious part of this? Somebody was saying something. Please.
It's too good.
No, but this is too good. Yeah, I understand that this is too good, but what is exactly we're doing wrong here? I want you to crystallize this. I want you to see that this is just not the way you do things. And I want somebody to say it out loud. Lena, can you please shed some light on that? Can you please explain what the hell am I? I'm right now violating one of the most fundamental laws of machine learning.
Well,
it's not just suspicious, it's just illegal.
Predicting on the training set.
Exactly. I do predict on a train. We have a very, very powerful model right now. It has depth of 100. It can model essentially everything into a separate bucket. Well, not exactly a separate bucket, but it's very powerful. And we use it to predict the training set, the very same data that has been used to train this data, to train this model, right? So when you train the model, it wraps the data up in the best way possible. So it is supposed to be good on this data. It's supposed to be, it was designed to be good on this data. But the question is not about how good is it on this data, but how good this model is on unseen data. This is I need to emphasize this. This is extremely important. And what I do here is the worst in the machine learning community. Doing this is completely prohibited. If you see somebody training and testing their models on their training data, you just can, you just have to stand up and leave the room. And there is nothing else to talk about. But since we were still, we were still in this kind of experimental conditions, I'm here showing you that you can use scikit-learn metrics. So instead of typing this all by yourself, you can use a mean squared error. So in scikit-learn, there is a mean squared error. Unfortunately, no root mean square error. So in order to get root mean square error, you can just run mean squared error, and then you can say, this is one thing, train fair amount, and this is what I predict. This is my DTR predict train, and you should get the same value. All right, then the values are the same. Now I urge you to submit it to Kaggle. So please submit this model that has shown us 2.59 in our training data to Kaggle and tell me what's the score. So by running these lines, you do it. Lena, what's the score of this model? Of this fakish, illegal, violating model?
I don't know. I need to fill my code with intercept, so like.
Oh, you don't need. Just jump over here and just start with the decision tree.
Oh, okay.
Don't waste your time on the rest of the things. Just come here. So everybody, what's the score? We've got 2.59. What is it?
It was slightly better than previous algorithm.
5.48.
5.48. So you can see that it has shown us amazing results on the training data. Amazing, absolutely amazing. And on the unseen data, it performs twice worse than the trained data. So Lena, I want you to see this. I want you to catch up with this. Did you run this decision tree part?
Mm-hmm. Yes.
Okay. Did you get your Kaggle submission of the decision tree model?
Maybe not.
Don't waste your time on writing the SQRT function. Just go ahead and use the scikit-learn implementation.
Okay.
Okay. In the meantime, I need to share my slides. So these are my slides. So what we have just encountered together with you is called overfitting. And can you guys see my slides? No, you can't see my slides, sorry. You should now see my slides. Okay,
yes,
you should see my slides. Sorry. So what we have encountered is called overfitting, and this is what you have seen many times. I hope that's the first time you see how it can hurt. It can really hurt, because we saw that the model was so good and we were expecting to get into top 100 or even better than that, because Igor said that we can get even higher than top 100. And we ended up being almost at the same position, which is like, you know what, it actually did happen to me personally. Once upon a time, I was training my models and I got my training data leaking into my validation data. So I got basically over-optimistic results, and I overpromised my team. I said that, guys, we are going to rock this competition. We are going to be the best. According to my validation results, we are the top notch. And then I submitted this model and it turned out to be worse than the previous submission. I can't describe you how frustrated was I. And this is what overfitting can do. And I mean, this is not the worst. It may just really wreck the performance of the model on unseen data. All right, so this is overfitting. How does it look like from theory perspective is that when we have a very simple model, like a linear regression, right? It's just a line. Under any circumstances, this line will become anything else than a line. So it will stay a line. And then we have something more sophisticated like decision tree. Under certain circumstances, decision tree, for example, you have seen it in our example, if you give it enough depth, it can be very flexible. It can wrap up the data so that it performs perfectly on the training data. So the question is obvious here is, what do you choose? Simple but imperfect, or complicated but ideal, right? So what kind of fit is best? So we have a red model and we have a blue model. In one ring, in one side of the ring, we have a simple linear regression. The other side, we have a very sophisticated decision tree algorithm. So how do people in practice work with these models is that they divide the training data into parts randomly. So they select 60% of the data and then they call it the training data, and then 40% of the data they call validation data set. You can also find validation data set sometimes called developing data set or for development or something like this. So what happens is that we fit the simple model, or sorry, the complicated model and the simple model, both of these models on the training data, right? So both of these models on the training data. Simon, could you tell me how does it look like? What is MSE of the perfect model? What's the MSE of the perfect model?
0.
0, exactly, because it perfectly wraps up the data, right? Oleg, could you please try to estimate what is an MSE of the red model? Given that this is one. This distance is one. This distance is one.
About 1.
Okay. No, this is one. This is one. This is true. Oleg is true. Is right. I mean, what happens is that we calculate MSE, right? The MSE is the mean squared error. The error here is 1. We square it, it's still 1. We square this error is still 1. We square this error is still 1. Then we sum them up and we divide by 3, which is 1, right? So MSE of the perfect model is 0, but MSE of the red model is 1. But now the main trick is what happens on the validation set, right? So we definitely would conclude that the blue model wins on the training data. This is what we have seen, right? The model, the blue model in our case performed with RMSE of 2.59. The red model performed, I don't remember. And now we basically use the same models without changing the models on the validation data. So we copy paste the perfect model in the validation data. And we also copy paste the red model on the validation data. And then we calculate the MSEs. Kenneth, what is MSE? What is mean squared error for the perfect model here?
Oh, so 4 plus root 5, something like that.
It's 5 divided by 2. So it's not RMSE. Let's not calculate RMSE, but just MSE.
Okay, so
you were right. So this one is 4 plus 1. So it's 5 divided by 2, right? That's the 2.5. And obviously the MSE of the red model is 0.5. This is just this 1 divided by 2, right? So this is 1 divided by 2. So we can see that validation data on validation data, the simple model here performed better, okay? So in this case, the reality, the way how the model will behave on the new data is more important than the way how the model performs on the training data. All right, so what you need to know is this one, the right part, not the left part. You don't really care about the left part so much, because what you do care is how your model behaves on unseen data, because that's where your business value is in new data, not in old data. Okay, the old stuff happened. Nobody cares about the old stuff anymore. What you care is about new stuff. All right, so there is a natural extension. Oh, by the way, do you have any questions regarding this? Igor, Lena, Kenneth?
Oh, all fine.
Sorry?
All fine, yeah. No
All
question.
fine, all fine. I've heard when. Kenneth, do you have a question?
Well, I mean, I could see there being like a kind of a practical effect, which is that you make a model in the trained data set and then you're validating it and then you see which one is better. And then you go back and you fiddle with your trained data set and you get a better thing. Then you validate it and you get slightly better ones. Then you pick that one. And I could see how you would just end up overfitting to your validation set eventually.
Absolutely, absolutely. So what Kenneth is saying is that having just one split is not enough, because that what actually happens, that people look at the validation performance and they're like, I don't really like that. What if I, play around a little bit with my data on my with my training model? What if I choose another model and then I validate and I see that it performs better than my previous model, so I will stick to this model. But this is essentially overfitting to your validation set. And in order to avoid this, people came up with a cross-validation algorithm. So the cross-validation algorithm, you take the entire data set of 100% data. Basically, you split it into something like 80-20. These splits depend on the size of the data. Sometimes you may split and hide more data. Sometimes you have no luxury and you need to hide less data. So you basically hide this test set and you never use until the final moment. And then what happens is you you divide your training data into chunks, into equal number of chunks, so that they are equal size. For example, 4 chunks in this case. So each chunk contains 20% of your data. You call one of these chunks a validation set, and the other 3 are your training data. You train your model on the training data, and you validate it on the validation chunk. Then you record your MSE, and then you shift the validation chunk. You call other 3 chunks of training data. You retrain the model, and then you validate it on a validation chunk, and you record the MSE. And you do it until all the chunks had a turn to be a validation chunk. You got 4 MSE recordings. You average them up, and this would be the kind of unbiased estimate of your model on your training data. So this is how you can say, this is what my model will produce eventually on my test data. So you basically, for example, you have 2 models. One is the linear regression, the other one is decision tree. You ran them through the cross-validation algorithm. You picked up the average MSE, and then you compared the average MSEs, and this would be the basis for your final decision, okay? That's how you decide which model do you keep. So there is another kind of small extension, is that you shuffle the data to get random false, right? So so for this model, you reshuffle the data, and for this model, you also reshuffle the data. So the instances that come into each of these chunks are different for both of these models. So this chunk here does not contain the same data as this chunk right here. Do you guys have questions about this?
Nope.
Okay, all is clear. So then I have a question. Igor, what if I have, let's say, KNN, K nearest neighbor, with different K values? Would you consider them to be different models, or is it the same model? For example, I have 3 values of K, 5, 10, and 50.
Well, it's the same algorithm, but they are different models because coefficients are different.
Yeah, the models are different, right? So, so for example, for KNN, you can have each one of them you can run through the cross-validation algorithm, and for example, record the average accuracy for each of these models, and then you can compare them, and you can, for example, decide that K was equals to 1 was performing the best in your data, so you keep that one. Okay, makes sense? Yeah, the same stuff. Choose the best model. The overall machine learning pipeline is the following. You acquire some data, you pre-process it, you choose the best model, you hide the test into the safe place, you run the cross-validation, and you find the best model. You take out the test from the safe and you run it, and that's how you get the final estimate of your model performance. That's like the final machine learning pipeline. Sometimes people skip this place. They just use a cross-validation algorithm as an ultimate, basically estimate of my model. This is called generalization performance. So the way how the model behaves on unseen data and the gap between train and test performances is called generalization performance. So how my model is generalizable to the unseen data. So let me go back to my collaboratory. Okay. So here I just propose to make the split into 80% and 20%. So here I say that let's consider, let's create a new variable train X and train Y. So the train X would contain the actual data and train Y would contain the labels. And I say, okay, let's take the first 80% of my data and I will call them train, okay? Here we go. And now I propose to use the remaining 20% and assign the remaining 20% into validation X and validation Y. Please fill up these 2 lines. I'll be slowly following you. So I need definitely, again, sample it from the train. So here I used 0 to 80%. But in this case, I actually should start with 80% and I should finish it with, oh, basically that's enough, basically. It's just one little caveat not to forget that here I do it for the fair amount. Let me run it and check that it works. Okay, so here we go.
But you shall assign 20%.
Yeah, to the validation set.
So it's at 0.8 now. We need to change it to 0.8.
That's okay.
Sorry? Oh, it's okay. That's okay. Let me send it to Slack and chat.
But why you have 0.8?
Because
80%?
Yes.
Of the length.
It is starting point. No.
Yeah.
This is my starting point, yeah.
Okay.
And then until the end. So this means until the end.
until
Okay.
the end, it's really 20%.
Yeah, yeah. So from 80% point onwards until the end of the data set. Let me copy that into Slack and copy it also to chat.
Oh, I see what you're saying.
Sorry?
So it's okay. Sorry, I understand now.
Okay. Okay, nice. I copied to both chat and Slack because, for example, Igor cannot have access to Slack. So I just make sure that everybody has the access to this code. Yeah, so let's check this out. Yeah, so we have 700,000 rows in the training and 200,000 rows in the, yeah, well, basically 800,000 in training and 200,000 in your validation sets, which is nice, which is what we wanted, right? So this is all we wanted. This is first 5 rows. There is one caveat here. Who can guess what's the caveat? What's the kind of something that maybe we want to avoid? Maybe not. It depends. What's the caveat with this kind of split?
It is not random.
It's not random. Exactly. We have just chosen first 80% of the rows. What could be the problem with this? Simon, what could be the problem?
For example, time of trip. Maybe at the beginning we have only morning trips and we do not take into account evening trips, for example, or weekends versus business days, etc.
Yeah, for example, if our data has seasonality, right? So we have only, let's say, summer months in our training data, while our test data is like winter months, which have a very different dynamics. Although it's very, it's highly debatable whether you need to do this kind of random split or you don't. But let's just practice. So let's just practice here. So what I propose here is to use this train test split. It's a function in scikit-learn that you can say, here's my train, here's my prediction value, and can you please randomly select 20% and assign it to the validation set here. So if I run this one now, by the way, what does the random state mean? Elena, can you tell me what's the random state equals to 111? What's the purpose of this line here?
I don't know.
Anybody? Igor, what's the purpose of this line?
Just a seed? Oh, sorry.
As far as I remember, this is well, random is not truly random because randomity should be like maybe chosen. Yeah. So in this case, we choose like a random like ID 111. In case we would like to obtain the same random
Split,
split,
right?
yeah, in a future.
Yeah, basically that's what Kenneth said, random seed. This is what you call random seed. Since as you were describing, Igor, you were saying that random is not really random, and it's exactly true in a sense that random generators are pseudo-random generators, and they can generate exactly the same random numbers given that we know what's the seed. So this is the seed for this random generation. So this ensures that every one of you guys have exactly the same random split, right? So we all have the same random split, and we can ensure by running the first 5 lines here, and you should be able to see the same first five lines as I do.
Yep.
Do you guys see the same lines?
Yes.
Yep.
And if you would use this different random state, or you would remove the random state, we would all see different lines here. That's what random seed is basically. That's what it's meant to ensure the reproducibility. This is called reproducibility, when you can rerun the experiment and it results in exactly the same results all over again. Okay. Any questions about this? All right. Now what we do is we use the decision tree regressor with somewhat more modest depth 10. We feed this decision tree on our train X. See the difference? This is a train X. It has 800,000 rows, not 1 million. And then we calculate the difference. We calculate the RMSE, the error on the train data. So here's the error on the train data, and here's the error on the validation data. All right. All right. So the error is not very big, right? The difference is not huge. It's okay. Now, Kenneth, what happens if I make the tree much deeper? What happens to this difference between these two errors?
To a point, it'll get farther apart. As you overfit, you'll get farther and farther apart.
You will get further apart. So your training performance will improve, while your validation performance will actually get worse, right? So what happens here? Oleg, can you explain in like very simple terms what happens? Why does, I understand why, I mean, this value gets better because we are getting deeper, but why this value gets worse? This is something counterintuitive. Why the hell is this happening?
Because in fact, yeah, this is no linear, let's say, dependency, yeah, and let's say you got overfitting, yeah, for the train, yeah, but on validation, let's say the curve is different, yeah, and that's why you don't get the same good result.
Yes, so I get very much fixated on the training data trend. I got very good performance. I learned very well what's the training data trend looks like, but this trend is not exactly the same in validation data. So when I try to be very, very flexible, I am basically missing a lot of details. This is exactly what happened, what we saw in the lecture slides, right? So when we have a perfect model that we copy onto the onto the validation data, and we saw that it actually performs much worse than the simpler models. So if we use the simpler models, for example, with the max depth 10, then we will see again that the gap between these will shrink, right? What happens now is that I want you to train a model, the decision tree model, on the entire training data. So without train and validation split, just on the entire data, and submit it to Kaggle and let me know where we are with respect to the previous results and the leaderboard. So just submit this to the Kaggle and tell me how far on top we are. Igor, you are traditionally the person to bring us the good news about us getting higher in the ranking. So are we? Did we improve?
4.02. So we are good.
So where we are we in the top 10 now?
No, not top 10, not even top 100.
Not even top 100.
But better than.
Are we in top 1,000 at least?
Let me see.
By the way, Igor comes back with the results much faster and faster.
Yay!
After every training, you see?
It's a human training, huh?
No, guys, don't be so like. Don't talk like
don't
that.
Be so optimistic.
Yeah, actually, this shift enter is it's a magic. Use this, please.
Shift enter makes people more efficient. You're seeing.
Yeah, makes
Lena,
you faster and faster. Yeah.
Igor, you should give Lena a small lecture about this because I have seen her clicking. I have seen her doing this clicking stuff. Lena, you shouldn't do clicking. You should do shift enter, shift enter, shift enter. Okay.
And you will be faster and faster, guys. Use
faster
that.
And faster and faster and faster.
Yeah,
all right. All right. I'm really glad that you did it. Actually, it's my personal type of pleasure. I teach a lot of biologists. So me personally, I give a lot of talks to biologists. I teach R. I teach R to medical doctors and biologists, and they do this kind of stuff, right? It's not just clicking. They're really afraid of that stuff. And when I see a person actually using shift enter, I'm like, this is the thing. This is a breakthrough. Anyway, I'm glad that we guys managed it. And well, 4.0 something that Igor said, it looks pretty nice. But as Kenneth mentioned, we are still somewhat violating the rule. We are still overfitting to the validation set. So for example, if one of you guys will be like, oh, goddamn, I can find a better number here and I can get better score on my validation set, it would still overfit your validation set because you will now tune the parameter to get a better performance on your validation set, which is a legal practice. So instead of doing this, one of your homework exercises, the homework exercise number 5, is actually about basically implementing the cross-validation algorithm. So the idea is that, can you guys go through all this depth here that I have encoded and try to estimate the RMSC for each one of these max depth of the tree and see if you can get even better with your decision tree performance, all right? So what I propose is, I propose to test each one of this as a max depth of the tree and use the 4 equal chunks, so cross-validation of 4 folds, and get the best model performing on Kaggle with the best max depth. So here I propose you to submit to the Kaggle and see if you get any better. Your last homework exercise for this homework, for this supervised learning homework, would be to do anything that is legally possible, something that you don't have to break the law of Ukraine or Canada or any other country to get to the highest position possible. So I listed some of the ideas that what you can try. In fact, we have had a file of 2 million rows. we have used only 1 million, so you can add twice more data to your training algorithm. You can do more pre-processing since we haven't really cleaned up the data. We did something, but not perfect. There are better distances that we can use. And I even give you a code of the harvest time distance. Does anyone know what is harvest time distance?
No.
Hover sign, sorry, hover sign. So I'm mispronouncing. So basically, when you take two points on the Earth's surface, that's the best approximation for the distance between these 2 points. Because if you just calculate the Euclidean distance, it will not be as good because the Earth is round, and then we don't really have a straight line between the points. We actually have something called hover sign distance. Okay, this function here is calculating in kilometers the distance between 2 points in hover sign distance in kilometers. Okay, between any 2 points on the Earth's surface. So you can use that one, and I urge you to do anything that is allowed by law to get to the highest possible rate. And I also encourage you to report your final leaderboard rank, and report whatever you have done to get to the highest to this point. So number of points that you will get will depend on your quality of your solution. And you have a bonus exercise. If you like to try it out, then you can play around with the bonus exercise as well. Any questions here about this homework, this part of the lecture? Because that's all for the supervised learning lecture. This is all we have for the supervised learning lecture. Lena, did you make it till the end?
Mm-hmm.
Uh-huh. You sure? All good?
Yep. Yep.
Any help needed? All right.
Well,
Any help? No? No? Okay, fine. I was too quick to shrug off this help question. I was like, okay, no help needed, so fine. Okay, so we reached regularization. Sorry, you can't see my slides. Sorry. Okay, here we go. So this is a regularization lecture. I will try to go into depth, into similar type of depth as we had in the supervised learning. Yeah, Simon, you had something.
Excuse me, once technical question about the previous topic. If I will play with all these algorithms and I will keep it in Kaggle under my login, I mean, is it okay from copyright point of view if I will keep it in my Kaggle?
I'm not sure. What do you mean by keep it in Kaggle? What do you mean?
Yeah, I mean, this code is not developed by me, but it was developed by you. And I will report it as algorithm.
Oh, don't worry about this. So the Kaggle competition that we are running is called the sandbox competition. So it basically is a competition that is meant to train to educate, right? So okay. It doesn't really matter. By the way, they are not checking your code. They are not checking your code. The only thing that they check is your submission file, right? So your predictions. They don't really know your code. They just look at your predictions. So they don't know your code, and it doesn't really matter so much. So don't worry about this.
Thank you.
And the competition is over, so there is no harm done anyway.
But how can you share your, let's say, achievement to other persons?
This is I would really encourage you to participate in active competitions. So let me okay, let's get back to the I'm glad that you guys asking questions, because when you say I don't have questions, it usually means that I have questions, but I'm not I'm not strong enough to say it out loud. So I do think that you need to look at the Kaggle competitions, because Kaggle competitions are something that is at the core of the machine learning community. We love Kaggle competitions. Especially myself, I participate in almost every Kaggle competition that is related somehow to health. For example, prostate cancer grade assessment. You got the histopathology slide. So this stuff on the image is the histopathology slide. And you develop a classification model that looks at the histopathology slide, and it makes a prediction whether this is a cancer and what kind of degree of the cancer it is. You learn a lot by doing this because there are plenty of people that participate. For example, there are 300 people, 363 teams who participate. And you can see that people share their code. These are people attempts to do something nice. So you can always, so if you are afraid of like, you don't feel strong enough to compete with real masters, then you can always look at the basic solutions. For example, somebody is saying, hey, this solution here will result in the leaderboard like that. For example, right? So this one, it's basically saying that if you do what I did, you will get 0.79 in the leaderboard. Let's go to the 0.79 leaderboard and see where the leaderboard. So 0.79 would result in, well, something like top 100. So just by following another person's kernel, you would end up in top 100 and you would be competing for the bronze medal in this competition. So all it takes is just to register yourself to the competition, train yourself to do some machine learning by following somebody else's advice, and then maybe improving upon this advice to get into a bit higher position. So that's all it takes. And you can follow the forums, you can follow the discussions, you can follow somebody else's kernels, you can publish your own kernels, and so on and so forth. This is so awesome. You learn so much from these Kaggle competitions. I do encourage you to participate. If you have time, if you have enthusiasm, it's gonna be absolutely adorable. Any other questions?
But again, so if it's active competition, let's say everybody can see your score, yeah, in the leadership. But if it's not active, then nobody will see it. Yeah.
Yes, that's true.
Okay.
That's the only thing you can do is to make a screenshot of your My Submissions page, and then
Photoshop it.
And no, I just say, and then just say with that submission score, I would end up in that place. But that's all you have. Yeah, that's all you have. That's the downside of participating in sandbox competitions that have finished. I'm still very grateful for Kaggle community to keep these competitions alive, because then I can train. I can use it as a classroom exercises, and they are pretty good as a classroom exercises. All right. In the meantime, any other questions? Igor, Simon, Kenneth, Elena, do you guys have any other questions?
No questions. I've just tried to use mine as depth for our algorithm, and I got better results than with 10. So actually I've completed my homework, so I can.
I think you can still get even better.
Maybe, yeah, we'll try.
See. Anyway, so regularization lecture. Let's see what the regularization lecture has for us. First of all, I wanted to emphasize that today I will upload homework number 2, and the deadline would be June 4th. You saw the way how the homework number 1 looked like. So the same, it would be very similar in the homework number 2 case. So a series of exercises that you can connect to the practice session. And what you all need to do is just export your Python notebook and submit it to the Moodle. That would be everything that requires for the homework. Any questions about homeworks and deadlines? Do you feel like this is enough? Because I was trying to be reasonable and sensible and try to put the deadline so that you actually have some time. I don't know, and the program manager didn't really tell me much about what are the courses that you have in parallel. So I don't really know what's your load at the moment. I know that you have some managerial course, right, that is running at the same time, but I'm not sure if you have a high load on that. So anyway, just let me know if you feel that these deadlines are not reasonable. We can always discuss, but I felt that 2 weeks or 3 weeks for one homework should be more or less enough to complete. Here, I posted a slide from my deep learning lecture. So this is one of my concluding slides from my deep learning lecture. And this is basically visualizing the way how neural networks are trained. So you have the training performance, right? This is loss is basically another way of saying error. And you have your validation performance. So you check them at the same time when you complete one iteration. Each iteration in deep learning is called epoch. I think you know it. And so we end up drawing this kind of curves, right? In deep learning, we end up drawing this kind of curves. And the difference here is what people call overfitting. All right. So one question that somebody may ask, and that would be a very legible question, is, so what should we do with this overfitting, right? So what are the ways to actually tackle this overfitting? And somebody can say, well, there's something clearly, there are at least two ways to look at the overfitting. And one of the ways is saying there is something wrong with the model. Since it overfits, so you're probably using a very complicated, very strong model. So you need to do something to your model to make sure that it doesn't really overfit. Another person may say this makes sense, but on the other hand, there is something wrong that can be with your data. Since, for example, you may have too little data. And you're using it all over again. That's why you're overfitting. Since your model sees the same data all over again, its training performance gets better because it just memorizes your training data, while your validation performance does not improve since you don't really show your validation data to your model, so it doesn't know about it. So it gets very good at predicting very small number of training examples, but it stays dumb when it comes to validation examples. So there are two major ways to look at this problem. And well, the third one is that you're looking at the wrong graph, but that's just a stupid joke. Basically, there are two ways. One is saying there is something wrong with the model. The other one is saying there is something wrong with the data. And in fact, we will be talking about both of these ways of looking at the problem. Let's call them initially way A and way B. And we will be, at the first half of the lecture, we'll be talking about way A methods, and in the second half, we'll be talking about way B methods. And these methods, so these regularization methods are not exclusive for deep neural networks. They are actually applicable, and they are applied in all sorts of machine learning models, in all sorts of machine learning algorithms, like decision tree, like regression models, like linear regression models, and so on and so forth. Okay. Yeah. So in the first half, we will concentrate on this way A methods. And way A methods is saying that your model is too quick, so I need to hold it back so that it doesn't really overfit. So I need to make the training harder for your model by adding something extra to the learning process. Let's consider some loss functions or error functions that we have seen before. These are, for example, for linear regression. Do you guys remember what is the error function that linear regression uses? What does linear regression tries to optimize? Simeon, do you remember what linear regression tries to optimize?
Mean square error.
It's almost there, but it's I think originally it uses something called least squares method, and it minimizes the sum of squares. So it's residual sum of squares. It's called residual sum of squares.
Residual, yes.
So this is called RSS, residual sum of squares. For example, for neural networks, many neural networks, when it comes to regression problems, they optimize MSE, mean squared error, and decision tree that we saw, it also minimizes mean squared error. Convolutional networks, when it comes to classification problems, they use something called BCE, Does any one of you guys know what BCE stands for? Kenneth, what is BCE?
I do not know, and I'm looking at the formula. I can't quickly determine.
Olena, do you know what BCE stands for?
No.
It is very easy. It is written on the screen in Russian. Все means all.
Okay, that's another way of looking at it. Igor, do you have any wild, what are the wild assumptions? What could be the BCE?
Before Christ era, Christ.
Oh, that's pretty cool. I love that one. So if nobody knows, then BCE stands for binary cross entropy. This is what binary cross entropy looks like. This is what mostly, when you train your convolutional neural network, I think you should have had a lecture about convolutional neural networks. So when you have a problem of detecting cats and differentiating pictures of cats from pictures of dogs, then BCE is the measure that you will be using to optimize this network. This would be the error function that you will calculate. We're not going to look into how exactly this is done, but you can take my word. So this is the function that this network will be optimizing. It's called BCE, or binary cross entropy error. All right, so these are all errors. So residual sum of squares, mean squared error, binary cross entropy error. And they tell us how far we are from the optimal model, right? So they tell us how, how wrong we are with our predictions. Let's recall the linear regression example. So I have here a linear regression example. This is the one that we were calculating yesterday. And this is the line equation. So we were basically saying that the line goes through this middle point, and then we calculated the x minus x mean, y minus y mean, and then we calculated the square of that one, and then we multiplied these two. It got some results. We recall this W1 is the division between sum of, this is called a covariance, and this is called variance, right? So covariance divided by variance, and we got 6 divided by 10, 0.6. So that was fine. Then we calculated the W0 just yesterday, exactly the same way, 2.2. And this is how we got the line, right? Now the main question here is, what is error of this line? What is residual sum of squares, which is RSS of this line? So how wrong we are, how bad we are, right? How far we are from the optimal model that would be perfect model. So what we do, we just calculate the sum of differences squared, right? So for each of these dots, we can, just to remind you that the green Y is the real value, which you can find on the Y-axis. So if you would project the point of the Y-axis, you would know what's the real value. And the predicted value is, Igor, what's the predicted value for this point here? For the point number 1, 2, 3, 4. What's the, okay, never mind. What's the predicted value for the first point here, this one?
Perpendicular к прямой. I don't know how to say it in English.
The predicted value is the point on the line here. The y-axis of the point on the line that you project this, the green point on the linear regression line, and the y-axis of this projected point is the predicted value, right? So this is what I'm going to tell you right now. N is obviously a number of points. So in our case, it's Olena.
5.
5, gotcha. So this would be, if you would write it up, this would be the equation. And for the first point, the real value is 2. And the predicted value, Oleg, what do you think? What is the, can you estimate what's the predicted value here?
About 3.
About 3, yeah, that's about 3. You can calculate it, right? How can you calculate, Kenneth? How can you calculate this this value?
2.2 plus 0.6 times the x we're calculating for. So
What is the x that we're calculating for?
1.
Exactly. So it's 2.2 plus 0.6 times 1. And it's basically 2.8, right? So you don't really need to guess, Oleg, and anybody. You guys don't need to guess. You can just use the line equation that we have calculated. You can substitute x for each of these points, and then you will calculate the y hat, which is the predicted value. All right? Which is, that's what we do, 2.8, right? So this 2.8, so 2 minus 2.8 is 0.8 squared. This minus 0.8 is exactly this perpendicular. Igor, you remember you said perpendicular to the line, and this is actually the residual. This is what is called residual. The length of this perpendicular is called residual. And the y-axis of the point on the line to which you projected this residual is with the predicted value of the point. Everybody, does this all make sense? Okay, gotcha. Go for a break. Come back at 12, and we will continue with the regularization methods. If it looks like a kindergarten stuff right now, that's all right, because we are moving on to, well, I'm hoping to say more complicated things, but no, I really don't like complicated things. I try to make things simple. So we are moving to some other kindergarten stuff, but so that you learn something on the way from one kindergarten to another kindergarten, all right? So see you in 10 minutes. Get your, stretch your legs and drink some water.